Okay, so that's a summary of the presentation. For sure, we didn't mention everything in this presentation because the report the data and the report are very huge. It's kind of a review paper, so we didn't mention everything. We just mentioned the essential things about the concept of the compressed air energy storage and its type and its technology. So first, we will talk about the need for storage. We know that there is an economical growth, and in order to keep this economical growth without affecting the environment, we need to search for a lot of solutions. And one of them, we need either to reduce the consumption or increase the efficiency of the energy already used, or we can switch to clean energy. And this clean energy is intermittent. The renewable energy solutions are intermittent. So we need to combine the energy storage with them in order to have stable energy when the demand. And okay, yeah. Okay. A lot of energy storage techniques are available. One of them is the batteries, different types of batteries, the pumped hydro storage, the compressed air, which is our topic for today, and the flow and the supercapacitors, which is a hot topic for the research today. Okay, first we passed this slide. Why storage? Why do we need storage? First, because it's provide electricity at short notice, so it having a fast response for the energy need. Instead of waiting for other sources to provide electricity, we can control the frequency using the storage. We can use the peak shaving and something called the black star effect. It's related to load management and reducing the fluctuation of the load. For sure, overcoming the intermittent nature renewable sources. And okay, it's backup power for emergency. So what's the compressed energy storage? It's a technology. It works like all the thermodynamic cycles by using compressors to compress air and then expansion in the turbine and used to heat sink and heat source. So it's during periods of excess of energy from any source of energy, air is compressed using compressor and stored in caverns, and we will see different types of storage. Then when we need this energy during the supply shortage, this air will be released and it will be expanded in turbine to provide electricity.
Hello, there are several types of compressed air energy storage. We have adiabatic, diabatic, and isothermal. For the first type of adiabatic, the term adiabatic refers to the process being thermally isolated, meaning there is minimal heat exchange with the surroundings during compression and expansion. In an adiabatic system, the heat generated during compression is stored and reused during the expansion phase, increasing thus the system's efficiency compared to traditional compressed air energy storage systems. Now, adiabatic compressed air energy storage systems is considered a promising technology for large-scale energy storage applications, but it is still in the early stages of development. There aren't existing plants that use adiabatic systems. However, there are existing plants that use the second type of systems, which are the diabatic systems. These systems minimize heat exchange with the surroundings, and they allow for heat exchange during compression and expansion processes. This system is generally less efficient in terms of energy conversion compared to adiabatic, but it can offer advantages in certain situations where a ready and cost-effective heat source is available. Now, for the third type of systems, which is the isothermal system. From its name, isothermal means constant temperature. This energy storage technology aims to maintain a constant temperature throughout the compression and expansion processes. In this system, the heat generated during compression is effectively removed to keep the air temperature constant. The key principle behind this system is to eliminate the temperature increase that occurs during compression, which can lead to energy losses in conventional compressed air energy storage systems. By maintaining a consistent temperature, this system seeks to improve the overall efficiency. Now we have two existing compressed air energy storage systems. The first one is the Huntorf plant. It is located in Germany, and it is the world's first operational plant. It was built in 1978, and it can power a capacity of about 290 megawatts. The second plant is the Macintosh plant located in Georgia. It is less efficient, and it was made in the 1990s, and it has the capacity of about 136 megawatts.
Okay, getting back to a slide, it should maybe we pass this slide. Ryan talked about the adiabatic systems. After the adiabatic systems, they are actually the last improvement in the compressed air energy storage is something called the advanced adiabatic compressed air energy storage, the AACAES. It's the same concept of the adiabatic energy storage, but with thermal energy storage. What will happen that when the air will be compressed, it will pass before being reserved, as shown in the figure here. Before being reserved, it will pass through a heat recovery or heat exchanger, and the heat will be stored in another liquid during the compression, and during the expansion, the air will pass through the heat exchanger again and will regain this heat before entering the turbine, which will increase its temperature before entering the turbine in order to generate electricity. Now
انا قاعد بالخنشاره.
هي بتذكر الفيلم بس
okay, guys, maybe there is please mute yourself. Okay, the operating principles. How does the CAES works? It works on three processes. First one is the compression process. For sure, the compression here, we need to compress the air for high pressures. So one compressor will not be enough. So we will be using two compressors, one for the low pressure compressor and another one for the high pressure. And the same for the turbines, we will be using two turbines. I will use the pointer here. You can see that first the air is being extracted from the atmosphere, and it will pass through two stages of compression. The first one, it will be in the high pressure compressor. It will enter here, pass by an intercooler, then it will be stored we have several types of storage, maybe in cavern for underground storage or in tanks for overground storage. And then it will, when the recuperator here represents the heat exchanger, when when electricity is needed, the air is released from the storage. It will pass by the recuperator and regain the heat again. Then it will pass to the turbine. Okay, we mentioned the expansion process through the two turbines also, and for sure, before entering the turbine, the heat recovery system is not enough to increase the temperature and the enthalpy of the heat for good results or for a huge amount of electricity to be supplied. So we need a heat exchanger. Mainly, we can use the natural gas for the combustion. or actually Macintosh and Hantroff use the natural gas for the combustion. Okay, for the air storage process, we can store the air in underground caverns, or we can use the overground, as we saw. And for the underground storage, we have several types. We have the salt, the hard rock, and the porous rock, and the depleted natural gas caverns. For sure, it depends on the area and the geology of the location where we need to store this air. Okay, we tackled first the categories of the compressed air. Here we need to differentiate between the categories and the techniques. The categories of the compressed air energy storage are based on the way that we treat the heat. If it's more related to temperature and heat. We saw the diabatic, the adiabatic, and the isothermic. But the techniques of the compressed air storage are more related to the nature of air used, or the storage of air, the ways of air storage. So we have 4 types, as we can see here.
The first type of air storage is isochoric storage. This air can be stored at constant volume. The condition of charge is revealed through variations in pressure. A vast salt cavern or a steel pressure tank are the two most typical examples of isochoric storage. The impact of isochoric system on the compression and expansion equipment is unfortunately one of the main drawbacks. Lower efficiencies result from these machines not working at their intended pressure ratio because they must adapt to changing pressure. The second type is the isobaric compressed air energy storage. Here, air can be stored at constant pressure. Now, for constant pressure storage to keep the pressure constant throughout charging and discharging, a variable volume is needed because we all know the equation PV equals nRT. If the volume is constant, we gotta change the other variable. So the level of charge in this scenario is indicated by the volume. Technically, it is possible to achieve constant pressure storage using, for instance, a hydraulically compensated reservoir in which pressure is roughly maintained constant by a second reservoir of liquid.
Okay, the third type is the liquid CAES, which means we can store air inside the tank in a liquid phase. How this can be done? During the compression stage, we can use a liquid. We can spray liquid inside the air and compress it to high pressures before being stored. Then, when we want to use this air to be expanded in the turbine, this liquid will be released again to the atmosphere, and the temperature of the air will increase through the combustor. This will increase the efficiency of the system and will increase also the storage density. Which means in smallest volume, we can store more quantity of air. The last one, which the supercritical CAES, it combines both the AACAES and LAES. Here we can store air again in a liquid phase, but now we will compress it to supercritical pressures in the same way, and this it's in the same way we can use the waste heat. Here there is a waste heat exchanger. The compression will be in 2 stages, and the same for the expansion. It's just a way to change the characteristics of the air to increase the efficiency and the storage density of the air. Okay, and now for the future development of CAES technologies, a lot of actually not a lot of future developments can be done because this storage system is a very old system, and now we are working on more advanced things related to batteries and to green hydrogen, to different topics. So compressed air energy storage is a very old topic, and now the research, there's not a lot of research about it. So concerning the future development, we can increase, mostly we can increase the efficiency of the equipments used, machinery, compressors, or even increase and improve the heat transfer processes that happens during the compression and before the compression and before the expansion processes. So we will tackle three future development: the turbo machinery, and the combination of CAES with renewable energy systems, and the thermal and storage.
Now, for compressors and rotors, internal leakage and energy losses are major issues in diminishing efficiency. To boost this system efficiency, we can boost the integrated heat recovery, where heat recovery systems within compressors and rotors capture and reuse excess heat generated during compression, further increasing the overall system efficiency. Also, we can use advanced materials, which such as high-strength alloys or composite materials, to improve the performance and durability of compressors and rotors. These materials could offer benefits in terms of weight reduction and increased efficiency. And at last, we can use variable speed compressors. Designing compressors with variable speed capabilities could optimize operation under varying load conditions, improving system flexibility and efficiency. Now, for turbines and expanders, there are advanced cooling techniques, which is the second slide. Yeah. Research may focus on novel cooling methods to manage the high temperatures generated during expansion, improving overall system efficiency. Also, we can use variable geometry expanders, which allows for optimization under varying load conditions and operating parameters. And that's it for rotors and expanders.
Okay, another technique that can improve the efficiency of the compressed air energy storage is dealing with the thermal energy storage. We know that during the heat recovery and heat exchange, a lot of heat will be lost, and the process is not ideal or isentropic. So a solution that we can suggest here is to use the PCM, the phase change material. Maybe we didn't study this process. It's just a suggestion inside the tanks. So when heat enters with very high pressure, and temperature, those this material will store the heat and re-give it again to the air before the expansion process. This will increase the efficiency, as the heat will be approximately to 92 to 93% delivered and exchanged through the air. And we can for sure use other techniques like the types of ropes where the air will be stored, depending on the physical and chemical properties of the material. And for concerning the combination, we can combine the compressed air energy storage. As Ryan said, there is no applied actually or implemented plants integrated with renewable energy. So as we know, most the two plants that are actually working are combined with gas turbines, and we can combine the compressed air energy storage with the solar energy, wind turbines, even with the solid oxide fuel cells, which are electrochemical material that can provide electricity just through the combustion. They use the combustion of air and oxygen to provide electricity. So instead of using the normal the normal combustion situation, we can implement or use those cells in order to benefit from this combustion to generate also electricity at the same time. Okay, that's this is a schematic for the combination with solar and wind, the suggested ones, and we're done. Thank you.
Okay, thank you, Omar, for your presentation. Do you hear me?
Yes, I can hear you, Doctor, and Ryan also.
Okay, Omar, great. Can you go please back with the slides?
Yes, okay, for sure. Here?
No, I will let you know where to stop. Go down, please.
I'm in the cover page.
Oh, yeah, go down, please.
Okay.
Okay, stop. Previous slide, please. Okay, Ryan, please give me more details about this cycle and explain in detail all the different steps that we have.
Yes, of course. So when we compress air, we can avail from the fact that there will be more pressure. And this pressure, this energy, we can use it. How could we use it? By directing this energy into turbines. When we direct this energy into turbines, we can generate electricity. But this isn't easy as said as it is done. There are several more processes we could use, as we learned from previous mechanical courses and previous cycles. We need to add heat so that it becomes more efficient. And as we add more heat, we need to also take away heat from condensators and several machines. And this is my explanation. Do you need anything else?
Can you give more details about why we use the intercooler, the aftercooler, why we use different two levels of turbines and two levels of compressors?
Two levels because we can boost efficiency more. So the intercoolers are for the low and high pressure compressors, rather than in the TS diagram or other graphs. They are split into two, and this way we could be more efficient. And same applies for the turbines. From the exhaust heat, we can use this heat to heat our compressed air. So this is all just to boost efficiency.
Okay, and what about the recuperator? Why we use it here?
The recuperator is used in the exhaust gases. This exhaust gases isn't directed to the atmosphere. We can use it and we can heat it. For example, not in this, but in another cycle, we can use it in a boiler and heat our parameter that needs to be heated. In our system, it is the air, because if we heat it more, it will become, we can produce more work from it.
Okay, thank you, Ryan. Omar, can you go down, please, with the slides?
Yes, Doctor, for sure.
Okay, Omar, yes.
Yes.
Please give more details about this cycle and its operation.
Okay, here this cycle works as all the compressed air energy storage cycles. First, we have the air extracted from the atmosphere. It goes to the first compressor. It will be compressed, and here there is something called a heat regenerator. It passes through it, and it will be a bit cooled. And here we can spray liquid. Usually they can use liquid nitrogen or water. And there is another compressor here just before the tank. Do you see the mouse? Okay.
Yes, I
There is
can.
another. Yes, there is
Yes.
another compressor here in order to recompress it again after mixing the air with the fluid or used. Then it will it could be done in 2 stages or 3 stages. It is mentioned in the report depending on the temperature of the air and its pressure and the environment, the ambient conditions around it. Then it will go to the tank. When we need to use the energy, this here the B is a blower. This blower is used during the expansion. So when we need this air again, it will be pumped because it is liquid. It will pass again during through the regenerator, and it will lose the water or the fluid. The concentration will decrease, and this blower here, its mission is to deliver this liquid outside the regenerator. Actually, I didn't go into the design of the regenerator. Then the dry air goes to the combustor, and when we can apply the liquid or a natural gas for the combustion, and it will go then to the turbine when we will use again the regenerator heat before delivering it to the atmosphere. And it will the cycle will repeat again. This part is the continuous of this part here.
Okay, Omar, thank you. Please, next slide.
Yes. Here.
Yes. Ryan, please elaborate more on this cycle. Ryan, do you hear me?
Yes, yes. So here we are using liquid, and the liquid, as we heat it, it can provide more energy. And from this energy, we can use it to provide more pressure. And in this way, we can provide more work. It seems difficult or complex, this process, but as I said, this is what happens.
Ryan, can you talk about, okay, you give an overall explanation, but what about the different components of the system? What is the function of each of these parts?
So to store the liquid, we need a tank, but this liquid shouldn't be contaminated. So there's a contaminant also. And there are several valves to regulate the liquid and the gases after the liquid is heated. Also, there are compressors, and heat is rejected to the atmosphere. And yes, that's it.
Omar, can you elaborate more, please?
Okay, doctor, I will describe the system actually. Here we have also two compression stages, also low and high. Here the air is compressed and it will go to the heat exchanger. Then the air it will be extracted again, the same as the liquid air compressed energy storage, and also for 2 or 3 stages. It depends also on the ambient conditions before being introduced inside the heat exchanger again, where this heat will store the heat. This device will store the heat from the air, and the air will be introduced in the contaminant here, and this tank is an expansion tank. Actually, this is a valve here because we are storing the air at high pressure, very high pressure. It's the critical pressure, and the contaminant from this side, some of the contaminant will be released to the atmosphere, and when we need this air, it will go from this side, and again it will regain the heat which released from in the first stage before going to the turbine and reheated again before going to the second turbine, and then generate electricity and deliver to the atmosphere from turbine number 1, which is the low pressure turbine.
Okay, thank you. Can you move down, please, with the slides?
Yes.
You talked about implementing, implementing
Yes.
renewable energy. Ryan,
Yes.
can you comment more, please, on how we can implement renewable energy and how efficient it was with these cycles of air compression?
As we now, Omar and I found out that compressed air energy storage systems alone isn't that efficient. It is more efficient when we combine it with other systems. That is, we can use it from solar energy. For instance, some systems, we need to heat the gas more. And how could we use heat others more efficiently than the sun's rays? So from the solar, we could extract the heat and heat it more. And in this way, it becomes more efficient and we could produce better electricity. Also, the thing is about supply and demand and energy density also. So at low peaks, we could store the air. And at high peaks, when energy is expensive, we could use this stored air that we stored it at lower cost and the solar energy as well, and produce electricity.
If you want to use wind, Ryan, okay, how will you use it here? At which level? It will help you into doing what?
We could generate several forms of energy from using wind. And one of these forms is mechanical energy. So rather than just relying on the output of the compressed air energy storage to produce electricity, we could also power the turbines that produce electricity from the wind. And these two systems complement each other.
Okay,
but you may ask the question. Oh,
yeah. Yes, tell me.
You may ask, why wouldn't we only rely on the compressed air energy storage? Because as I said before, it is sometimes efficient in the cost. At low energy demand, it is cheap. So at cheap times, we could put it with the wind and could make money. Thank you.
Okay. Omar, can you go down, please, with the slides?
Yes, doctor. Thank you.
Okay. Dear students, do you have any questions for Omar and Ryan about their work? Any question for Ryan and Omar? Okay, thank you, Omar and Ryan, for your presentation.
Doctor, can I
Yes.
mention something before
Yes.
leaving? Yes, here
Yes, Omar, sure.
Yes, there is also an important part here. Ryan mentioned in the presentation, but didn't mention again. Here there is something about the wind that it's intermittent, and the vibration or the fluctuation in the production is very high. So using the compressed air energy storage with it, will help to reduce this fluctuation. It will give something called or base something called the base load, which is a normal load that we can rely on all the day when designing the plant. So when during the supply and the peak supply time, when the velocity of the air is very high, we can store. And when the velocity decreases, the response of the compressed air energy storage is not long. So we can deliver the energy from the wind and at the same time from the compressed air to the load. And in this way, we have the supply, which is from the air and the compressed air equal to the load. That's a very important part regarding the renewable energy with the compressed energy storage, because they are very intermittent and we can't rely on them without storage at all. And already we mentioned the positive things about the compressed air energy storage. We still have 2 minutes if anyone wants to add anything or ask any question.
Okay. So I want to highlight the importance of such a project in the course, because in this presentation we incorporated first the, let's say, cycles. Okay, so we have seen incorporation of several cycles that we have already studied together in compressed air storage. Plus we can introduce from this project the use of renewable energy, because our next step will define first the use of fossil fuels. Okay, so here, for example, if we need to provide heat, one of the possible sources is fossil fuels. This is why the chapter that we'll tackle now is how fossil fuels, their characteristics, how we can use them, what are their disadvantages, so we can understand why we shift towards renewable energy. In this project, we have seen that renewable energy can be implemented to compression of air. So we can use solar energy, we can use wind energy, plus also in next chapters we'll define hydropower. So all of these sources can be used in any, if you want, any cycle, thermodynamic cycle. We can implement to it renewable energy to increase its efficiency. So we can consider that any of the projects that you are doing now is incorporating, if you want, the whole material from the thermodynamic cycles to the strategies to enhance the efficiency, to the use of renewable energy systems in order to use them instead of fossil fuels, to reduce greenhouse gas emissions and to reduce the bad effects of fossil fuels. Omar, the project is great, and Ryan, but what is missing mainly is an economical study about such systems. It is economically viable to implement them compared to other strategies. What is their status, etc. So I advise any